Good morning everyone. So today's session we are going to discuss about introduction to normal shock waves, right? So what is normal shock wave? So what we will be doing, basically dealing with these shock waves, where do we observe is that, so to deal with these supersonic shock waves, a class of shock waves, namely shocks that are oriented perpendicular to the flow. So means if it is, this is a flow, so perpendicular to that particular flow, that shocks which are oriented, that one we will be calling it as a normal shock waves, right? So a large number of supersonic flow problems will be involving with this normal shock wave. So most of the supersonic flow problems, we will be having the presence of the normal shock waves will be observed inside the flow, right? So where do we see, basically these are like examples, the gas properties at the nose of a blunted nose body moving at supersonic speeds are dictated by the flow through normal shock. So if you are taking the blunt nose body, moving at a supersonic speed, it means velocity will be higher, right? So velocity is more actually. So supersonic sonic speed means what we have seen in the previous session, that is 1. Supersonic speed means what we will be telling, that it is greater than 1.2, right, Mach number. So at this particular speed, what is happening is like, if the flow is going through the blunt body, on this particular one, there will be a formation of the shock wave will be occurring ahead of this body, that we will be calling it as a normal shock wave. So similarly, the inlets of some jet aircraft are designed to have a normal shock waves across their entrance. So that we will be calling it as a normal shock inlet. So if you are taking jet aircraft, so where inlets has been designed for that jet engines, so that is such a way they will be designed that normal shocks will be there at their entrance. So at the entrance of that particular inlet, we will be having the presence of normal shock. So that one we will be calling it as that particular inlet, normal shock inlets we are naming. So to know the basic behavior of the shock waves, what we will be doing is like one-dimensional flow we will be taking, and we will be finding the properties vary in only one direction. So in order to understand the behavior of the shock wave, what we are going to do is like, we treat the flow as one-dimensional. So we will be treating the flow as one-dimensional. So for this particular one, we will be seeing in the properties variation in one direction only. So suppose if it is in this x direction, if we are taking means, so whatever the properties are there before the shock wave and behind the shock wave, how it is going to vary, only in one direction we are going to see. So now imagine a flow constrained to vary in only one direction, where the stream tube of such a flow has constant area, such as flow through constant area duct. So what we are doing, we are flow constraint we are doing, where we will be having only flow in one direction. So where the streams tube of such flow is, so what the flow when it is going, it will be having the constant area. So there won't be any distortion in the area. Such flow through a constant area duct. It means like general what we can tell is like whatever the flow is, like constant area duct inside that flow is going. So what can cause the flow variable to change if the across the cross-sectional area of the flow remains constant? So what we are going to see is like, if that particular cross-sectional area, a flow variable should change if the cross-sectional area of the flow remains constant. So how it is going to change? We will see. So a normal shock wave is one case where the flow properties can change dramatically across the region thinner than the paper. So what we are telling, shock wave, right? So shock wave formation will be there. So what it is happening across this particular shock wave, there will be flow properties going to change. So the region which is there, so that region is very thinner than the paper. So within that region itself, there is going to be much changes in the flow properties, right? So also what we are going to consider also, if heat is added or taken away from the flow, one-dimensional flow with heat addition the flow properties will change. Suppose in this case, if you are taking the one-dimensional one, heat is going to adding or taken away from the flow. So that time what it will be there? One-dimensional flow with heat addition, and the flow properties is going to change. So if there is a frictional shear stress is tugging on the outside the boundary of the flow, such as friction at the wall of the duct, and one-dimensional flow with friction, the flow properties is going to change. If there is a frictional shear stress tugging on the outside of the boundary layer, means if you are taking this is a boundary, so outside the boundary layer, if there is a shear stress, frictional shear stress is tugging, such friction at the wall duct, one-dimensional flow with friction, the flow properties are going to change, right? So if one-dimensional flows are approximate models of real flows with heat addition and friction. So what we are telling, if one-dimensional flows are just approximate models, if you are considering of real flows, then what will be happening? We will be having a heat addition as well as a friction also we have to consider, right? So one-dimensional flow with heat addition is very useful for estimating the effect of burning in a jet engine combustor. Okay. So what we can do with one-dimensional flow with heat addition is there, means it is very useful to estimate the effect of burning. So inside the heat engine, how it is burning and what is the effect of the heat burning due to heat addition, extra heat adding to that particular system, right? So, and if you are taking the one-dimensional flow with friction, provides an excellent method for analysis of the gas flow through long pipes. So what we are doing? So one we are telling in the approximate models for real flows. So we are taking heat addition and friction, right? So with heat addition, what we are telling, we will be by adding heat addition, it is very useful so that we can estimate the effect of burning inside the jet engine combustor. So with adding the friction, what it is very useful is that we can analyze the gas flow through the pipe. So it means inside the pipe. So due to addition with the friction, how the properties are going to change, how it happens, what happens inside the pipe for the gas. So how the interaction will happen and all those things we can see only in one dimensional we can able to see. So these two are the approximate models of real flows with heat addition and friction we are considering. Okay. Now, coming to the history of this particular shock waves, where exactly has been observed and all those things. So on October 14, 1947, when Chunk Tiger pushed the Bell X-1 to speed slightly over Mach number. So when he has been taken the flight, what he did was like he crossed above Mach 1. So the flight has been crossed above Mach 1. So he entered a new flight regime. So if it is crossing above Mach 1 means what it is that the flight regime is going to change it to from sonic to the transonic or the supersonic condition, right? If it is less than 1.2, it is transonic condition. If it is above 1.2, we will be telling it as a supersonic condition. So at that new flight regime, where shock waves are dominating the flow field. So means what he did is like he crossed above the Mach number. So then the new flight regime has been observed. So where the dominant of shock waves has been seen, right, in the flow field. So at Mach 1.06, the bullet-shaped rocket-powered research airplane created a bow shock wave that was detached from the body slightly upstream of the nose. So what happened is like bullet-shaped rocket-powered research airplane. So they have taken the bullet-shaped. So how generally bullet will be there? So we have like this, right? So this is the bullet shape we can consider. So this bullet shaped rocket powered research airplane was created. Bow shock wave is created that was detached from the body slightly upstream. So means like this it has been created slightly upstream of the nose. So at Mach 1.06 for the bullet shaped rocket research airplane, a bow shock wave that was detached from the body has been observed, that is slightly upstream of the nose. So during later flight, what it had on March 26, 1945, again pushed XS from 1 to Mach 1.5 in a dive. So at a single itself, what he did is like from Mach 1 to 1.5 at single its push itself, he has been driven to that one. So how it will be observed? So at that particular at Mach 1.6, what we told at upstream, there is a presence of bow shock has been observed. So that is detached shock wave from the surface. Now when he reached to Mach 1.5, what is happened? We have the formation of a oblique shock wave that is directly attached to the body, right? So we are observing at 1.06, we have a detached shock wave which is presented upstream of the nose, and at Mach 1.5 directly when it has been taken, so it is like we have observed the attached oblique shock wave on the surface of a bullet shaped rocket research, right? So for this flight, the Mach number was high enough that shock wave was attached to the pointed nose of the aircraft. So for this flight, what we have taken, so Mach number is high enough so that what we are having, so previously at Mach is 1.06, so we have the detached bow shock is there. So at Mach 1.5, so what do we observe? So we have observed the presence of oblique shock, right, on that surface itself. So the difference between these two flows are the bow shock is normal to the free stream direction, whereas the attached shock wave is oblique to the free stream direction. So we can see at this particular one, the shock which we have formed is like this. So what the formation of this one, what it is nothing but it is normal to the free stream direction, right? So whereas this particular one, what is it at Mach 1.05? We will be having the attached shock wave that is oblique to the free stream conditions. If you see like this, it is going into a oblique. So but here it is like almost perpendicular to the flow direction. So this is the major difference what we have observed for this flight when it is at 1.06 Mach number and when it is at 1.45 Mach number. It means like varying the Mach number with the 0.4 itself, what we are having, we are seeing the bow shock is getting converted into the oblique shock wave on the surface of the body. This means as we are increasing the speed of the vehicle, what it is observed that it is going to change the shock wave pattern as well, right? So now for a blunt closed body in a supersonic flow, the bow shock wave is always detached from the body. So in case if you have taken any blunt body kind of thing, okay. So if you are taking this kind of a blunt body, so this blunt body if you have taken, so for this blunt body in a supersonic flow, what we will be having? We will be having the presence of bow shock, that is nothing but it will be always detached from the body. Means that it will be presented at the upstream. So upstream of the flow only the bow shock wave is going to present. Moreover, near the nose, the shock is nearly normal to the free stream. Away from the nose, the shock is gradually becomes the oblique. So now what we will be having, the near the nose it is going to come, it is that shock wave is nearly normal to the free stream. So away from the nose, the shock wave gradually it will be converting into the oblique shock waves, it will be observed. So further illustration we can see so this is so this is if you are taking that bow kind of shock wave, presence of the body. So this is example of Apollo command module. So the shock wave present we can see in this one. So now this one for a sharp nose, slender nose cone at a different angle of attack. So you can see here the presence of the what kind of shock waves? Oblique shock waves, right? So here for a wind tunnel model of the space shuttle also you can see the oblique shock wave formation. So it means the speed at higher speed, the body on the surface of the body we are going to see the formation of the shock waves will be observed. So due to why this formation of the shock waves will occur is because of the disturbance in the flow, right? So the portion of the shock waves in figure that are perpendicular to the free stream we will be calling it as a normal shock wave. So a normal shock wave is illustrated in the figure. So you can see in this figure. So this is the normal shock wave. So for the normal shock wave, what we will be taking? We will be taking a class of flow field, that is one-dimensional flow we are taking for this one. So by definition, one-dimensional flow in which the flow properties will vary in only one coordinate, that is function of x only. So what is p, rho, t and u? So these are a function of X itself, as we are considering it the one-dimensional flow, right? So now what we will be having? For sure, normal shock before ahead of the normal shock wave, we will be having the Mach number is less than Mach number, like actually Mach 1 we have the greater than 1. So behind the shock wave we are telling it will be less than 1. So it, and you can see here the flow properties we are having before the shock wave P1, T1, ρ1, U1, and we are telling the formation of shock wave will occur when we have the Mach number above, right? So for this one, what is going to happen behind the shock wave? There is a change in temperature, change in pressure, we can see change in the density, but once the shock crosses the flow crosses the shock wave, there is a change in velocity. It is going to reduce. If it is reducing means what we will be having? Behind the shock wave, we will be having the change in Mach number. So these are like internally we will give this condition. So behind the shock wave, depending on the shape and all those things after the normal shock wave and the conditions, the given condition at whatever the different type of conditions which is be there, but these will be the variations will be coming behind the shock wave. So mostly in oblique shock waves, where we are going to see is for the two-dimensional phenomena we will be observing. So now what we will be doing, we will be considering the two stream tubes we are going to consider. So one-dimensional flow will be illustrated where the flow field variables are function of X only. So whatever the flow field variables are there, so that is this is nothing but flow field variables, okay. So these flow field variables are function of X only we are stating. So on the other hand, what do we have? We have many problems wherein the stream tube are varies with X only. So in another certain section, what we can deal is like stream tube area will vary with X only. So the condition of the area it is going to vary with respect to X only. So for such variable area stream tube, nature dictates the flow field in a three-dimensional flow where the flow properties are the functions of X, Y, Z. So normally what we are telling that two streams tubes we are considering. For that, one-dimensional flow is illustrated where flow field variables whatever we are going to take, it's only function of X, and because of that one what we can tell is like that area will be the constant area will be. So that is for one. Another stream tube which we are going to consider, many problems wherein we will be having that stream tube varies with X. So area of that stream tube what we are going to consider, so with respect to X it is going to vary. So for such a variable stream tube, nature will be dictating the flow dimension as 3 dimensions. Since it is going to change its area, it is not constant. So what nature is dictating that particular kind of flow field as a 3-dimensional flow field. So where flow properties are going to change in the function of X, Y and Z, right? However, if the variation of A equal to A of X is gradual, so if it is area is gradual, it is often convenient and sufficiently accurate to neglect the Y and Z flow variation. So in case if the area is gradual, if it is going to change the variation of the area, then we can neglect the YZ flow condition. To assume that the flow properties are function of X only, which is equivalent to assuming the uniform properties across the flow at every situation. So by assuming this particular one where the variation of A equal to A of X is gradual, then we are like for convenient and for sufficiently accurate purpose, we are telling that Y and Z flow conditions are going to neglect. So to assume that flow properties are function of X only, to assume that it is only X function, then what we are doing, which is equivalently assuming that uniform properties across the flow. So means the flow properties will be across the flow will be uniform, means it will be same at every section. If you are taking so at any section, if it is there, uniform properties will be there at every section of X it is there. Such a flow where the area varies A equal to A of X, but where it is assumed that P, T, U are only function of X only, this defined as a quasi one-dimensional flow. So where the area will be varying with respect to gradually will be there, but assuming P, rho and this is rho, P, T are you are only function of X, that we will be calling it as a quasi one-dimensional flow. Okay, so what it means, like the area which is there, it is gradually going to change. You can tell, like gradual variation is there. For this one, we are already assuming that whatever the flow properties will be there, it is constant at every section of uniform properties is going to be there. We are assuming that at every X section, we will be having the uniform properties will be there. So such a flow, what we are calling, we will be calling it as a quasi one-dimensional flow. So you can see here, A equal to constant, P equal to P of X, here rho of X, T equal to T of, means all these are, area is constant. So one-dimensional flow, there won't be any change will be there. And with respect to that one, we will be having the flow properties are also in the function of X only. So now if you see here, what it is happening here, the area is gradually increasing, right? So here the gradually increasing of area is there. So when this gradual increasing is there, what we are telling? We are telling Y and Z direction flow conditions are being neglected. So if you are assuming, if you are neglecting that one, by assuming that A equal to A of X varies gradually. So what we are telling? At every section of X, there will be uniform properties are going to observe at every section of X, right? So that is the main thing. So one-dimensional flow means where area is constant. So area is constant, whereas quasi one-dimensional flow means A varies with respect to S gradually. Okay, there is no sudden change, but gradually, step by step, it is going to increase. So while assuming that one, rest of the two direction we are telling there will be a neglecting of the properties, then what we are doing, since we have observed this one, assumed this one, we are telling that the flow properties are function of X only, and which is equivalent to assuming the uniform properties across the flow at every X section we are going to observe this one. So this is for the one-dimensional flow, and this one is for the one-dimensional flow, this one is for the quasi one-dimensional flow. This is all about, so what is normal shock wave, basically where they have been observed. So then what we have seen for the normal for with sharp nose supersonic vehicle, where bullet shaped kind of thing is there. For that one, we have at Mach 1.06, we will have seen the detached shock wave, which is almost of the normal to the direction of the flow, that shock wave. And what we have seen, then we have seen at Mach is 1.5, we have observed there will be attached shock wave on the surface, that is for the flow direction it will be in the oblique one. So if we are taking the blunt body, means we are having the blow shock wave will be forming upstream of the flow, and as it passes, then we will be slightly observing the oblique shock wave formation. And we have seen for two different cases where we will be having the sharp kind of edge nose, then we will be having the oblique shock formation will be there, and for the space shuttle, how the formation of shock waves will be over on it, how it will be there, we have been seen. So coming after that one, what we have seen ahead of the shock wave, we will be having the different flow properties will be there behind the shock wave, depending on the condition. Since we don't know the condition, based on that one, the flow properties are going to vary. So how it is going to vary is like pressure ahead of the shock wave, we will be having some value, but compared to the behind the shock wave, the pressure will be more, then density will be more, and temperature will be more, but behind the shock wave there will be a decrease in the velocity we will be observing, as well as the Mach number decrement will be there. That is the behind the shock wave. So then we have seen the two dimensions of the two streams tubes if we are considering, means one we are telling constant area will be there, another one is like varies with the X gradually. So with constant area we will be having the one dimensional flow, and with various area gradually, we are telling that one of the factor we are considering that it is since it is varying gradually, we are staying neglecting the y and z flow direction for our convenient and sufficiently accurate purpose. So then what we are doing, since to assume that flow properties are function of x only, we are telling that assuming uniform properties will be there at every x station, at every x direction or x station we will be calling it. So those are those flow, such kind of flow what is nothing but quasi one dimensional flow we are considering it, right? So this is all about the introduction for this particular normal shock waves.
Like, share and subscribe. Hit the bell icon for more updates.